this video, we're going to start chapter 4. The first part of chapter 4 is talking about different types of chemical bonds. And chemical bonds are those connections between atoms in our compound. So remember, a compound is a pure substance made up of atoms of more than one type of element. So water would be an example of a compound. And in water, I actually have a connection between oxygen and hydrogen, and then that same oxygen and another hydrogen. And these lines that are representing the connection between oxygen and hydrogen are chemical bonds. So chemical bonds are those connections. So the connections between atoms in a compound. And there's three main types of chemical bonds, and I'm just going to list them here, and then we'll go into more detail on a few of them. So our first one, ionic. And we'll give a quick definition. In an ionic bond, we actually have a transfer of electrons between atoms. So one electron is going to lose an electron and become positively charged. Another atom is going to gain an electron, or more than one electron, and become negatively charged. Now I have two oppositely charged ions. Remember, ions are charged atoms, and they're attracted to each other. So we have a transfer of electrons between atoms, resulting in oppositely charged ions. Again, remember, ions were charged atoms, which are then attracted to each other. Typically, it's going to be going to form between a metallic element and a non-metallic element. It doesn't have to be. That's not our definition, right? The definition of an ionic bond is that we have a transfer of electrons, right? Something is going to lose them. Another one is going to gain them, resulting in oppositely charged particles that are then attracted to each other. And then where does that usually form? It typically forms between a metal and a non-metal. And again, it doesn't have to be, but that's where it typically forms. And for us, I will stick to that. If I give you an example of a compound and ask you what type of bond it has, we'll generally get to say a ionic bond if it's between a metal and a non-metal. There is an exception to that, and that's polyatomic ions. So, or if there are polyatomic ions, it could still have a metal and then maybe a negatively charged polyatomic ion, but an exception or an example where you're not going to see that is if I had, let's say, ammonium chloride. NH4 with a positive charge is ammonium. It is a polyatomic ion that you are going to be expected to learn in this chapter. You probably have encountered it before, you just haven't had to memorize it until now. But nitrogen's a nonmetal, hydrogen's a nonmetal, and then chlorine is also a nonmetal. So this would be an example of something where I have an ionic bond, but I don't have a metal. So be careful. You don't have to have a metal and a nonmetal. You just have to have oppositely charged particles. So ammonium has a positive charge. Chlorine becomes chloride, it has a negative charge, and then I have oppositely charged particles that are attracted to each other. So just be careful for that, right? At first glance, one would think, okay, it's all nonmetals and probably not pick ionic bonds, but this does have them. A more common example, we could do calcium chloride. We will learn to name compounds in this chapter too, which is something that hopefully you've done in the past. I know if you had 130, you did. Hopefully your high school class did also. So we do it rather quickly, but we will review it. Calcium chloride, I have calcium, which is going to lose 2 electrons. Chlorine actually only wants to gain 1 electron each, so I actually need 2 of those. So I have calcium with an ionic bond to the 2 chlorides. So ionic bonds, a transfer of electrons, oppositely charged particles, oppositely charged atoms or ions, or I could have polyatomic ions, right? A group of atoms that function collectively as an ion. And then those opposite charges are attracted to each other, right? Positive to the negative, resulting in our ionic bond. Our second type is covalent. And in a covalent bond, we're actually going to share electrons. So instead of one atom losing them and another atom accepting them, we are going to share them. So the bonding electrons are shared between the atoms in the bond. And typically forms between a nonmetal, so a non-metallic element, and another nonmetal. And again, it doesn't have to be, right? If I asked you the definition of a covalent bond, you wouldn't say it's between a nonmetal and another nonmetal. That's not my definition, right? It's where it typically forms. My definition, we're sharing electrons between the atoms in the bond. Typically, it does occur between a nonmetal and another nonmetal. So the water example I drew earlier, oxygen is a nonmetal, hydrogen is also a nonmetal, so those electrons between oxygen and hydrogen are shared between those two. And then the third type we're not going to really spend any time on other than to mention it right now, and those are metallic bonds. And we are sharing electrons in metallic bonds. We're even sharing them more than we're sharing them in covalent bonds. We like to say that they're delocalized. They're kind of spread out. If I have like a solid metal, they're spread out over the entire solid. For this one, instead of even giving you a definition, I'm just going to tell you typically where it forms. You probably will never guess, but it's going to form between a metal and another metal. So it forms between a metal and another metal. And again, we're not going to really spend any time on it. I just want you to know that it does exist and then where it typically forms. We are sharing electrons. Ionic bonds first. So our metals, our metallic elements, these are going to be the ones that tend to lose electrons. Which means they're going to become positively charged. And remember, a cation is our positively charged ion. Or a positively charged atom, right? An ion is a charged atom, so positively charged atom would be an ion. So tend to lose electrons. They're going to form our cations. For main group metals, remember we subdivided our periodic table into main groups, transition metals, and intertransition metals. So for main group metals, we should put metals there. They tend to lose electrons from their highest energy occupied orbital. This is going to be different for most transition metals, so do be careful on this. So main group metals tend to lose electrons from their highest energy occupied orbital. And then the number of electrons that they lose is the number of electrons that they need to lose to achieve an octet. I'm going to write this a few different ways. Filled valence shell. I do have to define the word valence for us yet. And then also we could say a stable noble gas electron configuration. So the number of electrons that they lose is the number of electrons that they need to lose to achieve an octet, a filled valence shell, stable noble gas electron configuration. Essentially, it's all of those things. It's just that not all filled valence shells have an octet, so we can't always use octet. We generally can use stable noble gas electron configuration. Be really careful to not say it becomes noble gas. It does not. It's not losing protons, right? It's only losing electrons. So lithium with a +1 charge has the same electron configuration as helium, but it has not become helium. Lithium with a +2 charge still has 3 protons, helium has 2. So be really careful when explaining these. If you say it's becoming a noble gas, I'm not going to give you any credit for it because it is not, right? We're not changing the number of protons. We're only changing the number of electrons. The number of protons, remember, is what defines an atom as belonging to a particular element. So to become helium, it would have to lose a proton, not just an electron. So do be careful on that wording. So octet. And this is all should be review for you. If you had 130, I know you had this, and then hopefully you did in your high school too also. But an octet is 8 valence shell electrons. And again, I do need to define valence shell if you have forgotten what that means. So 8 valence shell electrons. So an octet, a filled valence shell, noble gas electron configurations tend to be more stable. Things want to be stable. Remember we said that filled and half-filled subshells are more stable? A filled shell is even better. If we can fill a shell, it's super happy. So a filled shell, noble gases tend to have filled shells, so that makes them stable. And then often an octet will give you that, just not always true. So an octet, 8 valence shell electrons. So what a valence shell is. A valence shell is our, we could say outermost shell. It's often defined that way, but that can be confusing. I'll write it, but I'm going to define it a couple different ways. A lot of times they'll say it that way in lower level classes. Basically, it's your highest value for N that has electrons in it. So your highest value for N, right? That has electrons. And then if you were saying valence electrons, that's the number of electrons in a valence shell. So just a couple examples to make sure that we're good with that terminology. If I was to look at, I didn't want a highlighter. If I was to look at lithium and I was to draw its electron configuration, 1s2, 2s1. So if I look at my values for N, remember those are my numbers here. I have a 1 and I have a 2. 2 is bigger than 1, so my valence shell is shell 2. And then my number of valence electrons is the number of electrons in that shell which is 1, right? I have 1 electron in my second shell with lithium. If I was to look at chlorine, and I'm going to draw our noble gas shortcut, I have 3s2, 3p5. And if I wasn't to draw the shortcut, now that I drew it, I'm going to do it again without it, just so you can see the difference. 1s2, 2s2, 2p6, 3s2, 3p5. Right, my valence shell is my highest value for N, so it's going to be shell 3, right? I have a 1, I have shell 2, and I have shell 3. 3 is bigger than those other numbers, so my valence shell is shell 3. And then the number of valence electrons, be careful for this. How many valence electrons do I have? Yeah, if you said 7, good. Right? It's the number of electrons in my third shell. I'm not differentiating between subshells here. So I have 5 here, right? That's in the third shell. I have 2 here, that's still in the third shell. So that gives me 7 valence electrons total. We talked about inner shell electrons in the last chapter. These all here that I just put the pink bracket around, these would all be inner shell electrons. Back up just to make sure everyone here is still with me, right? We're talking about ionic bonds. Ionic bonds are the attraction between oppositely charged atoms, or it could be groups of atoms in the case of polyatomic ions. So something's going to lose electrons, become positively charged. Something else gains them, becomes negatively charged, and then those are attracted. We had said our metals, these are the ones that are going to lose electrons, which means they're going to have a positive charge. And the name of a positively charged ion or atom is a cation. So a cation is an atom that has lost electrons. How many electrons does an atom lose? Well, it's going to lose the number that it needs to lose to have a filled valence shell, to have an octet. There are some exception to that, however. You could say to have the same electron configuration as a noble gas. All of those things are going to make it more stable. So an octet was at 8 valence electrons. Remember, if your outermost shell, if your valence shell is shell 1, you can't have 8 electrons, right? The first shell can only hold 2. We could write that in here. The exception, the first shell, right, n is equal to 1, can only have 2 electrons, and that's the maximum, right? It can have less. It just can't have more than 2. So I can't have 8 in the first shell. And then this stuff we had just talked about. So for our transition metals, they're still metals, so they're still going to tend to lose electrons. They're going to form cations. But instead of losing them, if I go back up here to my main groups, we said they're going to lose them from their highest energy occupied orbital. For my transition metals, these are going to actually lose them from the valence shell first, which isn't always the highest energy occupied orbital, and then it will lose it from the higher energy orbital if it needs to. So it's going to lose electrons from the valence shell first. And then the highest energy orbital if needed. So an example for this one is iron. And I'm going to kind of draw a strange mix of using the noble gas electron configuration. So if I go up, if I find iron on the periodic table and then go up 1 period, I would have argon. So if I was to use the normal noble gas shortcut, I would do argon and then 4s2, 3d1. I'm counting on the periodic table here. 1, 2, 3, 4, 5, 6. So 3d6. I want to draw a little bit more out without drawing the whole entire thing. So this would be the proper way to write the configuration. What I'm going to do is I'm going to go up one more period, and I'm going to write that noble gas, which is neon. And then I'm going to write everything that comes after that. Just because I want to show those also. So I just want to show a little bit more out, but I'm being too lazy to write out the entire thing. So if I said to write the electron configuration and I gave you the okay to use the noble gas shortcut notation, this would be the correct way to do it. Okay, so for these ones, the part that you need to notice is that my highest energy orbital, remember when we're writing these, energy is increasing in this direction, right? Energy is increasing left to right when we write our electron configurations. So my highest energy orbital right here is going to be a 3d orbital, right? It's the one that's furthest. However, my valence shell is shell 4. Remember that d orbitals are higher in energy than the s orbital of the next shell. So if I was to take them from my highest energy orbital, I would take them from that 3d, right? Because of the shape, they're higher in energy than those 4 s's. However, for transition metals, our rule says that we're going to lose it from the valence shell first. So if I want to write iron with a +2 charge, I'm going to remove 2 electrons, right? If it has a +2, it's lost 2. I'm using kind of my weird mix of notation here again. And I need to take these ones. Those are the ones that are going to go away. So I'm then going to write 3d6. So that would be my electron configuration for iron 2+. Iron is a variable charge metal. It can also form a 3+ ion, so I can lose 3 electrons. If I do that, we're still going to lose those 2 electrons in the 4s orbital, but then I will go take it from my highest energy, which are those 3ds, and then this would become 3d5. So if I go back up to the original one, I lost these ones, and then I lost one of those, so that became a 5. So again, you're going to lose from the valence shell first. Just be careful because our valence shell, right, isn't the highest energy shell with these transition metals. So just watch out for that. That will kind of goof people up. Between my +2 and my +3, which one of those do we actually like better? If you guys notice that this is half filled and picked iron with a 3+ charge, you were correct, right? I have a half filled d subshell. Remember there's 5 different d orbitals, right? Because I have 5 values for m sub l when l is equal to 2, which is what it's equal to when it's d. Because of that, I can have 10 electrons total, right? 2 electrons per orbital. So 10 would be full, 5 is half of 10, so a half-filled d subshell. So iron with a +3 charge is a little more stable than iron with a +2 charge. Again, just be careful. For transition metals, we're taking them from the valence shell first. If I go up and look at my definition for valence shell, it's the means you erase it, we meant to look at it. It's the highest value for N. So if I go back down, my highest value for N here is 4, right? I have a 3, and then I have a 4. So do be careful. And then the reason I wanted to write it kind of weird like this is if I asked how many valence shell electrons do we have in iron 3+, 3 is my valence shell. I just want to do this for practice. So I have 2 here, I have 6 here, and then I have 5 here. So that gives me 13 valence electrons. And then this one, I have 2, I have 6, and another 6. So that gives me 14. So just be careful. The reason I wanted to do this is I'm asking, a reason, you can't use octet as your explanation for this one because I don't have 8 valence shell electrons, right? I have 14 and 13. So again, just be careful in your wording when I ask you to explain these. Sometimes you can use octet, sometimes you could use noble gas. This is neither one of those. So again, just pay attention to what the situation requires for your explanation. Our nonmetals, let's talk about the ones that are gaining electrons. So these tend to gain electrons. Which means they're going to form my anions, which are negatively charged atoms or negatively charged ions. If it has a charge, it is an ion, so you can say it either way. So negatively charged, right, is gaining electrons. Electrons are negative. So be careful, it's gaining, which is making it negative. It's a common mistake to say positive, but remember electrons have a negative charge. And then very similar to what we were doing with our metals, right? Our metals for our main groups, our metals are losing electrons. They're losing the number that they need to lose, right? To have a filled valence shell, an octet, unless it's in the first shell, then it's 2 electrons, a stable noble gas electron configuration. And again, those are for the main groups. For the transition metals, it's a little bit different. Those tend to form different charges. They're variable charge metals. So these nonmetals, what they're going to do is they're going to gain the number of electrons they need to gain to have an octet, filled valence shell, stable noble gas electron configuration, all of those things. They're just gaining instead of losing. So they gain the number of electrons that they need to gain to achieve an octet. Again, be careful, only 2 electrons maximum in first shell. Stable noble gas electron configuration. We could say filled valence shell, just be careful because that's not always true neither. If it's the first shell or the second shell, it's probably going to be full. Third shell, maybe, probably not. Remember, you do have d orbitals in the third shell. So we can use fluorine as our example. 1s2, 2s2, 2p5. And we are putting them in, I didn't write that up above, but we're putting the electrons into the lowest energy unoccupied orbital. So I have room, remember my p subshell can hold 6 electrons and I only have 5. So I have room for 1 more. So that would be my lowest energy, and it's not that it's unoccupied, the lowest energy orbital that has room for more. So since this has room for 1 more electron, I'm going to put it there. I'm not going to go and throw it in a 3s. Right? I'm going to follow Aufbau principle and I'm going to put them in my lowest energy orbitals. So fluorine, because it has room for 1 more, right? It doesn't have room for 2 more. It has room for 1 more, is going to have a -1 charge. So 1s2, 2s2, 2p6. And this actually meets all of our criteria above, right? If I look, this is my valence shell. It is full. That's the maximum number of electrons I can put in the second shell, right? I don't have d orbitals in the second shell. So I have a filled valence shell. It's an octet, right? I have 2 electrons in the s subshell, 6 electrons in the p subshell, so that's 8 electrons total. And then it also has the same electron configuration as neon. If I was to look at nitrogen, 1s2, 2s2, 2p3, this time I have room for 3 more electrons, right? It needs 3 electrons to have an octet, which means it's going to gain 3, right? The number of electrons that it gains is the number of electrons it needs to gain to meet that criteria. So if I put 3 more in there, it has a filled valence shell, it has the same electron configuration as neon, it has an octet. So neon, I forgot to put my 3 there, is going to gain 3 electrons and have a -3 charge. Again, remember when we're writing charge, we do put the number first and then the sign. So again, I have an octet, I have a filled valence shell, it has the same electron configuration as neon. Again, be careful, don't say it's become neon, it has not, right? To be neon, it would have to have 10 protons, and nitrogen with a -3 charge still has 7 protons. Let's do a couple more, just writing electron configurations for different ions. So let's write the electron configuration for, let's do sulfur with a -2 charge. I'm just going to list a couple of them here. Nickel with a +1 charge, and barium, and I want you to guess the charge on this one. And it's not guess, I want you to tell me the charge. You're not guessing because I just told you why it is. So what is the charge? Why? And then draw the configuration. So for all of these, I really would like you to try them on your own. So please hit pause, draw these configurations, electron configurations, and then when you're ready to check, hit play again. Okay guys, hopefully you did that. So sulfur has a -2 charge, and I could have done the same thing that I did with barium. I could have asked you what the charge is, why, and then to draw the configuration. So I'm going to draw the electron configuration for just sulfur first, and then I'll add the 2 electrons to show you the charge. So 1s2, 2s2, 2p6, 3s2, and then 3p4 if I was just drawing sulfur, not sulfur with the -2 charge, so just plain sulfur. I have 4 electrons in that p subshell. Remember, my p subshell can hold 6 electrons, so I have room for 2 more, so it's going to gain those 2 electrons, and that's why it has a -2 charge, right? It needs 2 more electrons to have an octet. You can't use filled valence shell this time because remember in the 3rd shell I actually do have d orbitals. So I would have to have 18 electrons to have a filled valence shell this time, right? My valence shell is shell 3. But you could say it needed, that should say 2, like the number 2, the wrong version 2 there, needs 2 more electrons to have an octet, or you could say a noble gas electron configuration. Either one of those would work. So if I did ask why, that would be my answer. Nickel is a transition metal, so because of that, it actually can form, it can form more than one cation. Sometimes it loses 1 electron, sometimes it loses more than 1. We don't really have a rule for being able to determine it, so I wouldn't ask you what the charge is on nickel. But if I gave you the charge, I would ask you to draw the electron configuration, which is what we're doing here. And for most of these, I usually just draw the regular configuration first, and then I'm going to remove electron. I find that I make less mistakes if I do that. So drawing out nickel, and if you guys use the shortcut for this one, that's fine. I was going to tell you that and I forgot. If you didn't, then great, it's good practice. 4s2, and then I'm counting on my periodic table right now. 2, 3, 4, 5, 6, 7, 8. So 3d8. And again, that's plain nickel. That's without a charge. I am asking you to draw it with a +1 charge. And then remember, we take it from the valence shell first. My valence shell for nickel here is shell 4, right? For my main group metals, we take it from the highest energy orbital. For my transition metals, my highest energy orbital is not my valence shell. It is with main groups. So we're going to take it from the valence shell first. If it helps, just always remember to take it from the valence shell, because for main groups, we'll do barium next. My valence shell is my highest energy shell. But nickel with a +1 would have this one. If you took it from here, again, be careful. It's just that different rule that we have for transition metals, so watch out for that. So barium, I'm going to draw the electron configuration for the entire thing. So actually, I'm going to use this shortcut. So Xeon, this one's long. If you drew out the whole thing, then great. Actually, let's do it, because if you did the whole thing, I want you to be able to check your work. So let's do it. Oops, sorry, I made that kind of little. Now I'm out of my size is all out of whack. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then we get our 3ds, so 3d10, 4p6, 5s2, 4d10, and we're going down here because I've run out of room, 5p6, 6s2. So this would be my configuration if I did the entire thing. And actually, I am gonna squish it up here. I'm just gonna write this a little bit smaller so it'll fit. So 4d10. Oops, forgot my p's. 5p6, and then 6s2. And that gets me to barium. So it wants to know, what is my charge? This is a main group metal, so we are going to lose electrons from my highest energy shell, or highest energy orbital, which also happens to be my valence shell right now, right? Because my highest shell number is 6, that's going to be my valence shell. Remember, my highest value for N. If I remove these 2 electrons, if I remove these 2 electrons, then it's going to have the same electron configuration as Xeon, right? It's going to have that stable configuration. I would actually have an octet at that point, because once I get rid of those, let's actually do it, right? Once I get rid of those, my valence shell is now shell 5, and I have 2 electrons here and 6 electrons here, so I do have an octet. So what's my charge? +2. Why? Because that's the number of electrons that it needs to lose to have an octet, to have the same electron configuration as a noble gas, making it more stable. And then draw the configuration. We just did it right there. When we form an ionic bond, so when an ionic bond is formed, the number of electrons lost must equal the number of electrons gained. So remember, one of my atoms is losing electrons, generally going to be a metal. Another one is going to be gaining those electrons, generally a non-metal. And the number of electrons lost by my metal must equal the number of electrons gained by my non-metal. We're not going to have electrons just flying off and disappearing, right? I can't lose more than something else is gaining them. And I can't have them just materializing out of nowhere, right? Something can't gain more than something else loses. So whenever we form an ionic bond, the number of electrons lost must be equal to the number of electrons gained. So my metal needs to lose the same number that my non-metal is gaining, or non-metals are gaining. We can have more than one. Exception, again, watch out for polyatomic ions. I'm using metal and non-metal, but ionic bonds can also involve polyatomic ions. However we look at it, our net charge, this is really important, must be 0. Right? If something's losing 2 electrons and then it's going to have a +2 charge. Something else gains 2 electrons, I'm going to have a -2 charge. That total is going to be 0. So whenever we form an ionic bond, the net charge between the cations and the anions must be 0. If it's not 0, you messed it up. I'm not saying usually is 0 or is typically 0. I'm saying it must be 0. So the number of electrons gained must equal the number of electrons lost, which means my net charge must be 0. So an example, right? If I want to form a compound, and again, this stuff should be review. I know for a fact at 130 we do it because I teach 130 sometimes and we cover it. I'm not sure you did in high school, but you should have written ionic compounds at some point. So this is a pretty quick review. I'm just going to do probably 2 examples, but if you need to spend more time on this, please do. So the compound formed between, let's do barium, because we just talked about the charge on that, and chlorine. So barium wants to lose 2 electrons, right? It actually has 2 electrons when it's plain barium in its valence shell. If I was to look at the electron configuration for barium, and I'm just drawing my noble gas shortcut, I have xenon, and then I have 6s2. Right? I have 2 valence shell electrons. It's going to lose those to have that stable noble gas electron configuration, to have an octet. So barium wants to lose 2 electrons. Chlorine, however, if I was to draw the electron configuration for chlorine, and I'm going to use the shortcut again, so I have neon, and then 3s2, 3p5, it only has room for 1 electron, but barium wants to lose 2, right? Barium needs to lose 2 to be more stable. Chlorine needs to gain 1 to be more stable. I know that the number of electrons lost must equal the number of electrons gained, which means I'm going to actually need 2 chlorines for every 1 barium, right? If I only have 1 chlorine and 1 barium, I'm going to have a +2 charge, right? I wouldn't have this, a +1 charge. I would have this, which has a +2, this, which has a -1, so I'd have a net charge of +1. I know my net charge has to be equal to 0, so I need 2 chlorine. So a compound formed between barium and chlorine is going to have 1 barium and then 2 chloride ions. We are going to learn to name in the next video, so chlorine will become chloride. If I wanted to form a compound between potassium and oxygen, so potassium, and I'm just using the shortcut again, I would have argon and then 4s1, so 1 valence shell electron, right? It wants to lose this 1 electron, right? If it lost that electron, right, potassium with a +1 charge, it would have the same electron configuration as argon. It would have that octet. Oxygen, I have 4 electrons in that p subshell. It can hold 6, so it wants to gain 2 electrons, right? If it gains the 2 electrons, I now have an octet. I have the same electron configuration as neon. It's more stable when it gains 2 electrons, right? There's room there for 2 more. So because potassium is only going to lose 1, but oxygen's going to gain 2, I'm actually going to need 2 potassium for every 1 oxygen. So when I put these together in my ionic compound, if I go back up to this one, I have 1 barium and then I have 2 chloride ions, so BaCl2. Between potassium and oxygen, here I have 2 potassium, so K2, and then 1 oxygen, so K2O. So do be careful when we're writing these compounds, right? The number of electrons lost must equal the number of electrons gained. My net charge must be equal to 0.